Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss Physics Laws of Motion Part 1. Before we start our today's discussion, we request you to please subscribe, like and share our YouTube channel among your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Let us begin today's discussion. Before we start with laws of motion, we should have some fundamental ideas of force. So let us see what is force. Force is an external activity which pushes or pulls a body or tends to change the state of rest or of uniform motion of a body. The SI unit of force is Newton. It can be expressed as kilogram meter per second square. Therefore, we can write 1 Newton is equal to 1 kilogram meter per second square. Now, what are the characteristics of force? So, there are four important characteristics of force. It produces or tries to produce motion in a body at rest. Second, it stops or tries to stop a moving body. Third, it changes or tries to changes the direction of the motion of the body. And fourth, it can produce a change in the shape of the body. Depending upon the origin, force can be classified as a field force or contact force. So, what is field force? Bodies can exert force on each other without actually physically contact with each other. This is known as action as a distance, as action at a distance. Such force are known as non-contact force or field force. Example of field force can be gravitational force, electrostatic force. The earth applies the gravitational force on a mass which is known as weight. Magnitude of weight W is equal to mg, where m is the mass of the body and g is the magnitude of the free falling acceleration on the surface of the earth. Its value is 9.8 meter per second square. Direction of weight is taken towards the vertically downward direction, but actually it acts towards the center of the earth. So this is all about field forces. Now, contact force. The force exerted by one surface over the surface of another body when they are physically in contact with each other are known as contact force. If two surfaces that are in contact with perfectly smooth, which are perfectly smooth, then the entire contact force will act along the perpendicular, that is normal to the surface of contact, and is known as normal force or normal reaction. If two surfaces that are in contact are rough surfaces, then the component of the contact force acts perpendicular to the surface of contact, and other component of this force acts tangentially to the surface of contact, and this component is known as force of friction. Examples of contact force are normal reaction, tension, friction, etc. Now we'll study the content of this lesson because we have done the review portions. What is force, field force, contact force, characteristics of force, these are done. Now let us see the laws of motion. First we'll study and try to understand Aristotle's fallacy. Aristotle, a Greek philosopher, gave an gave a theory that an external force is required to keep a body in motion. But this was wrong because an arrow shot in a vacuum chamber does not instantly drop to the floor as soon as it leaves the bow. Afterwards, the idea and laws of Aristotle was proven wrong by Galileo and Newton. Galileo and Newton realized that a force would only be needed to change the motion of a body, not to make it move continuously and uniformly. Now let us see the law of inertia. A body at rest continues to remain at rest, and a body in motion continues to move with a uniform velocity unless compelled by some external forces. This property of body is known as inertia. According to Newton's first law of motion, every body continues to be in its state of rest or of uniform motion if in a straight line unless compelled by some external force. Therefore, it is similar to that of law of inertia. Let us study more about inertia. Inertia and mass. Heavier body has larger inertia than lighter body. So, if the mass is more, inertia is more. If the mass is less, inertia is less. Inertia and its types. So there are three types of inertia. inertia at rest, inertia at motion, of direction. Let us see each of them. First, inertia of rest. It is an inability of a body by virtue of which it cannot move by itself. A body at rest remains at rest and cannot start moving on its own due to inertia of rest. Applications. A passenger in a bus falls backward when it starts suddenly. This is because the sudden start of bus brings motion to the bus as well as to our feet in contact with the floor of the bus. But the rest of the body opposes this motion because of inertia of rest as they fall backwards. Second application. When a horse starts suddenly, the rider falls backward due to inertia of rest. Third application. When we shake the branches of a fruit tree, the fruit falls down due to the inertia of rest. Next application. We hit a carpet with a stick to remove the dirt or dust particle due to inertia of rest. The second point is inertia at motion. It is inability of a body in motion to stop by itself. A body in uniform motion can neither get accelerated nor get retarded on its own. It also cannot come to rest on its own. Let us try to understand few applications. First, a ball thrown upward in a train moving with uniform velocity returns to the thrower because during the upward and downward motion the ball also moves along horizontal with the train due to inertia of motion. Hence, it covers the same horizontal distance as the train does and ball returns to the thrower. Second application. A man jumping from moving bus falls forward due to inertia of motion. As his feet touch the ground, lower portion of the body comes to rest, while the remaining portion of the body keep on moving. As a result, he falls down in the direction of motion of the bus. Due, this is due to the inertia of motion of upper part of the passenger's body. Third application. An athlete runs some distance before taking a long jump due to the inertia of motion since length of jump depends upon its velocity at the instant of jump. Inertia of direction. It is inability of a body by virtue of which it cannot change its direction of motion by itself. Let us try to see few of its application. When a car makes a sharp turn at a high speed, the driver tends to get thrown on other side due to the directional inertia. When the car moving in the straight line, the driver tends to continue in straight line motion. When The unbalanced force is applied by the engine to change the direction of the motion of the car. The driver slips to one side of the seats due to the inertia of our body. Next application, the sparks coming out of a grinding stone are tangentially to the rotating stone due to directional inertia. Third application, the mud from the wheel of a moving vehicle flies off tangentially. So this is all about type of inertias. Now let us see different types of forces. In the review at the starting of the lesson, we have seen the definition, characteristics, and field force and contact force. So let us do a simple review for field different types of forces. So there are two types of forces. One is field force and other is contact force. Field force, mm, bodies can exert forces on each other without actually without actual physical contact. This is known as action at a distance. Such forces are known as non-contact forces or field forces. Example of such forces are gravitational forces, electrostatic forces, etc. Contact force. The force exerted by one surface over the other surface or when they are physically in contact with each other is known as contact force. If two surfaces that are in contact are perfectly smooth, then the entire contact force will act along the perpendicular, that is normal to the surface of contact, and is known as normal force or normal reaction. If two surfaces that are in contact are rough surface, then one component of contact force acts perpendicular to the surface of contact and other component of the force acts tangential to the surface of contact, and this component is known as force of friction. Normal reaction, tension, friction, etc. are the example of various contact forces. Now, normal reaction. The normal reaction perpendicular acts to the direction which is perpendicular to the point of contact. Tension. When a string, thread or wire is held tight, the end of the string or thread or wire pulls on whatever body are attached to them in the direction of the string. This force is known as tension. When the string is massless, then the tension has the same magnitude at all the points throughout the string. If always acts it always acts away from the body, it is tied to it. It is tied to. If it pulls on both sides of the body and same magnitude at same magnitude T, even if the cord turns around a massless, frictionless pulley. Such a pulley has negligible mass compared to the other body of the system and are negligible and has negligible friction opposing its rotation. Momentum. It is measured as the product of mass of a body and its velocity. It is a vector quantity. It is represented by P. P is equal to m into V, m multiplied by V. SI unit of momentum is kg meter per second. So let us see the graph for each of the case in momentum. When m is constant, p is directly proportional to v. So graph will be a straight line passing through the origin, where x-axis is v and y-axis is p. Case 2. When v is constant, p is directly proportional to m, where the graph comes a straight line where m is in the x-axis and p represents the y-axis. Case 3. When two bodies are of unequal masses have equal momentum, then v is inversely proportional to m or in directly proportional to 1 by m. That is, v1 by v2 is equal to m2 by m1. Newton's second law of motion, which states that the rate of change of momentum of a body is directly proportional to the applied force, and it takes place in the direction which the force acts. Consider a body of mass m moving with some initial velocity v. If an unbalanced force F is applied, the velocity will change from v to v plus delta v. The change in momentum will be delta v is equal to m multiplied by delta p. The change in momentum will be delta p, which is equal to m multiplied by delta v, which changes from initial momentum p of p to final momentum p plus delta p. According to Newton's second law of motion, F is directly proportional to rate of change of momentum, that is change of momentum, that is delta p upon rate, that means delta t. Therefore, we can write F is equal to k delta p is divided by delta t, where k is the proportionality constant. Taking the limit delta t tends to 0, then term delta p upon delta t becomes derivatives of p with respect to t denoted by delta p upon delta v delta t delta p upon delta t. F is equal to k multiplied by delta p upon delta t. So we can write p is equal to delta v. Therefore, F is equal to k multiplied by d delta v upon delta t. F is equal to km dv by dt. F is equal to kma, since a is equal to dv by dt. Taking by taking k is equal to 1, we can write F is equal to ma. Now let us see what is resultant force. When two or more forces act on a body simultaneously, then a single force, which produce the same effect as produced by all the force which acting together in is known as resultant force. Therefore, say F1, F2, F3 and F4 are acting on a body. Then the resultant force F is equal to F1 plus F2 plus F3 plus F4. Balanced force. When a number of forces acting simultaneously on a body do not bringing do not bring about any change in its state of rest or of uniform motion along the straight line, then the force acting on the body are said to be balanced force. In this case, different boxes, different forces acting on the box are given zero resultant. Balanced force do not produce any acceleration. Now let us see unbalanced force. When a number of force acting simultaneously on a body and bring about a change in its state of rest or of uniform motion along a straight line, then this forces acting on the body is said to be unbalanced force. Impulse. Impulse is defined as change in momentum. It is measured as the product of average force and time. It is a vector quantity and its direction is same as that of force. F is equal to ma is equal to m v2 minus v1 upon t2 minus t1 is equal to m bracket v2 minus v1, or we can write mv2 as v2 and mv1 as p1 and t2 minus upon t2 minus t2 t1. In the next step, we can cross multiply and we can write f multiplied by t2 minus t1 is equal to p2 minus p1. F multiplied by t2 minus t1 is called impulse. Put t1 is equal to t2 is equal to put t2 minus t1 as t, then impulse I is equal to f multiplied by t. SI unit of impulse I is equal to F multiplied by T. So SI unit of impulse is Newton second. Newton's third law of motion and its application. Oh, before we start Newton's third law of motion, let us see few of the application of Newton's second law of motion. So first application, cricket player lower his hand while catching the ball. The player increase the time during which the high velocity of the moving ball reduced to zero. Therefore, F is directly proportional to T, and where we can write the change in momentum. Uh, so we can write F multiplied by T is equal to change in momentum, that is m b minus u. U is very large. The initial velocity of the ball is very large. The final velocity comes to 0, v is equal to 0. Therefore, m multiplied by v minus u is fixed. If we increase the time, the f decreases. So the force of impact on the palm of the fielder reduces. Second application, a karate player can break a plate of tiles with a single blow of his hand because he strike the pile of tiles with his hard fast very fast, during which the entire momentum of the fast moving hand is reduced to zero in a very short interval of time. Third application, in a high jump athletic event, the athletes are followed to fall either on a sand bed or cushionized bed. This is because to increase the time of athlete fall to stop after making a very high jump, which decreases the rate of change of momentum and decreases the force of impact. Next application. While driving car, the driver and other passengers are advised to wear seat belts. Now let us see Newton's third law of motion. Every action there is always a equal and opposite reaction. Application of Newton's third law of motion. Recoiling of a gun. When a bullet is fired from a gun, it exerts forward force on the bullet and bullet exerts a equal and opposite backward force on the gun, due to which due to high mass of the gun moves a little duplicate backward and given a backward jerk to the shoulder of the gunman. Second application, it is difficult to walk on a sand or ice. Third application, jet aeroplanes and rockets. Jet engine in, in jet engine and rockets, the fuel burned to produce large quantity of hot gases. These hot gases comes out of a nozzle with a great force. According to the third law of motion, the equal and opposite reaction pushes the jet plane or rocket upward with a great speed. Conservation of momentum. For an isolated system, initial momentum of a system is equal to final momentum of the system. For example, consider a block A or object A and B of masses m1 and m2 moving along the same direction at different velocities u1 and u2 respectively. If u1 is greater than u2, then they collide with, and during collision A exerts a force F21 on B and simultaneously B exerts a force F12 on A. Let v1 and v2 are the velocities of the two objects A and B after collision, and they are moving along the same straight line. The momentum of B before collision Pb is equal to m2 u2. The momentum of B after collision Pb is equal to m2 v2. Rate of change of momentum of B is equal to the force by A and B, that is F21 is equal to m2 v2 minus m2 u2 upon T, which is equal to m2 v2 m2 bracket v2 minus u2 upon T. Similarly, the rate of change of momentum is of A is equal to the force by B on A, that is F12. So we can write F12 is equal to m1 v1 minus u1 upon T. According to Newton's third law of motion, the force F12 action must be equal and opposite to F21 reaction. Therefore, F12 is equal to minus F21, which is equal to m1 v1 minus u1 upon T is equal to minus m2 v2 minus u2 upon T. Therefore, we can say that m1 v1 minus m1 u1 is equal to minus m2 v2 plus m2 v2. Total momentum before collision is equal to total momentum after collision. Spring force. Whenever a spring is compressed or elongate, the elastic force developed in the string, which helps spring to restore its original length, is known as spring force. Force in the extended or compressed spring is proportional to the magnitude of extension for the compression, extension or the compression. That is, F is directly proportional to X, where X is the elongation or compression. F is equal to minus Kx, where K is positive constant called spring constant. Negative sign indicates that the force is applied in the negative sign indicates that the force is opposite to the displacement from the unstressed or uncompressed state. Now let us see few basic concepts. Tension in a string. The tension T is assumed to be constant throughout the string and is equal to applied force if the mass of the string is negligible or if the string is in equilibrium. However, if string has a mass, tension at different point will be different. The tension of two sides of any cross section of the spring is equal and opposite. Therefore, massless string has some tension T throughout its length such that T is equal to F as given in the below figure. The string has a mass. It also has some tension T at each point because A is equal to 0 and string is in equilibrium. In this case also T is equal to F as shown in the below figure. So the string has a mass and is accelerating. In this case, the tension of the string decreases as one moves opposite to direction of the acceleration. So string has a mass and is accelerating. In this case, the tension in the string decreases as one moves opposite to the direction of acceleration. In the below figure, T2 is less than T1. In the below figure, strings are assumed massless, then T2 is less than T1 and T1 is less than F. In the below figure, T1 is equal to T2. In the below figure, T1 is equal to T2 if pulley and strings are massless. T1 is greater than T2 if string is massless but pulley is rough and had mass, and M1 is greater than M2. Here M1 is greater than M2. Therefore, T1 is also greater than T2. Normal reaction. Normal reaction is a contact force between two surfaces in contact which is always perpendicular to the surface of contact. The following diagram shows the normal reaction between the two surfaces. In the below diagram, the weight of a block acting downward and the ground push block of pushback of the block with reaction force R. Here, weight of the block is equal to reaction force R, that is mg is equal to R. In the below figure, N1 and N2 are the normal reaction of the ground on the stone. Next one, in the below figure, normal force on the block is shown below. In the below figure, forces on the slope are shown. So we need to draw a free diagram to find out the force first. So there are 3 points of contacts. So in the below figure we can see the free body diagram. So all the points where the sphere is touching the surfaces, which are three points, normal N1, N2 and N3 are drawn for that. The weight is acting as mg. Similarly, the points of contact of the rectangular block over the sphere is given by. So weight is acting directly downward. Normal force F3 and F4 are acting normal to the point of touch. Equilibrium of a particle. A body is in equilibrium when it is not at rest or moving with constant velocity in an inertial frame of reference. At equilibrium, the vector sum of the force acting on it must be 0. Sigma F is equal to 0. Application of Newton's law of motion. Case 1. If a mass is hanging from the ceiling, then by free body diagram we can write uh, T, the tension of the string is acting upward and weight mg is acting downward. A. When the system is stationary, then T is equal to mg. B. When the system moves up with acceleration a, then T is equal to mg plus ma. C. system moves downward with acceleration a, that is T is equal to mg minus ma. Case 2, when a uniform rope of mass mg is hanging. So as shown in the figure, the stationary system, the tension Tx is equal to mx gx upon L. B, accelerating upward, then Tx is equal to mx up x mx multiplied by x upon L g plus a. C, accelerating downward, then tension Tx is equal to mx multiplied by x upon L g minus a. Case 3, we can see in the figure that in stationary we have tension Tx is equal to ms gx upon L plus mg. Accelerating upward, then Tx is equal to ms x upon L plus m multiplied by g plus a. Accelerating downward is equal to Tx is equal to ms x upon L plus m g minus a multiplied by g minus a. Case 4. Due to the weight of block, a contact force or normal reaction develops between block and platform. So, free body diagram, that is FBD of block with respect to ground, can be drawn below, can be seen below. So N is the contact force between the block M and platform. Mg is the weight which is acting downward. So free body diagram with respect to ground, we can write N, we can see the normal reaction of the block, N which is bound by MSG, again the normal reaction by the ground, and 1. N1 is the normal reaction between the ground. A, if the above platform which we have seen in the figure is not stationary, then net force is 0, that is normal is equal to mg, normal N is equal to mg, and N plus msg is equal to N1. B, if the system accelerates upward with an acceleration a, net force is given by, that is F is equal to N minus mg. So in the system accelerates upward with an acceleration a, net force is given by F is equal to m N minus mg is equal to ma. See, if the system accelerates downward with acceleration a, net force is given by F is equal to mg minus n is equal to ma. So case 5, two blocks are connected by a light inextensible string as shown. So let the tension in the string be M, be T. The free body diagram of the blocks of the string of the blocks and string are shown below. So M1G is acting downward, N1 is the normal force is acting upward, which is balancing the weight, and T is acting towards the string. In the second figure, M2G is acting downward, N2 is the reaction force acting upward and which is balancing the weight, F is acting towards right, T is acting towards left, which is balancing F. And the third figure is of the string. So T is acting on the right side. Again, a balancing T is acting on the left side of the string. So this is the free body diagram of the two blocks and the string. So extension of each block is A, and A is equal to F by M plus M. Second, the Newton's second law of motion for M1, T is equal to M1A. Putting the value of A, we get M1 F by M1 plus M2. Case 6. Tension in the block at a direction x from left and is given by if force is applied on the right end. So from the we'll draw the free body diagram for the system, then with blocks and etc. Then we'll write Tx is equal to Ma, Tx is equal to M x upon L multiplied by F by M. Instead of F, we can after solving we can get Fx by L. Case 7. Tension in the block at a distance x from the right end is given by Tx is equal to Fl minus x upon L. Case 8. Force applied by both right and left end. The tension x is equal to Tx is equal to F1x upon L plus F2L minus x. Case 9. Let F1 and F2 be the contact force between M1 and M2 and M2 and M3 respectively. The acceleration of the system is given by A is equal to F by M1 plus M2 plus M3. Case 10. The string are massless. Then for the below figure, we can write A is equal to F by M1 plus M2 plus M3. T1 is equal to, we can write M2 plus M3 multiplied by F upon M1 plus M2 plus M3. T2 we can write M3 multiplied by F upon M1 plus M2 plus F3. M3. Free body diagram of M3, that is M3G is acting downward, vertically downward. Normal force N3 is acting vertically upward. F2 is acting towards right. So F2 is equal to M3A. Free body diagram of M2 and M3 is given by M2G and M3G are acting vertically downward for block M2 and M3 respectively. N2 and N1 are the reaction force for block M2 and M3 respectively. Force F1 is acting towards right, uh, and acceleration is acting towards right. Acceleration is towards right in the direction of the force. So we can write F1 is equal to M2 plus M3 up multiplied by A. F2 is equal to M3 upon M1 plus M2 plus M3 multiplied by F. F1 is equal to M2 plus M3 upon M1 plus M2 plus M3 multiplied by F. Pulley and string. Case 1. Two bodies of mass M1 and M2, M1 is greater than M2, are connected by a massless string and moving over a massless frictionless pulley as shown in the below figure. If they are allowed to move freely, they move with common magnitude of acceleration A. T is equal to tension on the acting on the string, m1 is accelerated downward and m2 is accelerated upward. So let us see the figure and try to figure out. So here we can see uh, the proposed description in the figure. Equation of motion of m1 is m1 g minus t is equal to m1 a, which is equation 1. Equation of motion of m2 is t minus m2 g is equal to m2 a. Adding equation 1 and 2, we get a is equal to m1 minus m2 upon m1 plus m2 g. This is equation 3. Putting the value of equation 3 in equation 1, we get t is equal to 2 m1 m2 upon m1 plus m2 multiplied by g. As the pulley is rest, therefore net force on the pulley is 0. As the pulley is rest, therefore net force on the pulley is 0. Therefore F is equal to 2t, that is 4 m1 m2 upon m1 plus m2 g. Case 2. When two blocks of masses m1 and m2 are connected by a string passing over a frictionless pulley, and m1 is held on a frictionless table and m2 is suspended over the other end as shown in the figure, we can then write for m1, we can write t is equal to ma, and r is equal to m1g for equation 2. For m2 we can write t m2 g minus t is equal to m2a, equation number 3, putting the value of t from 1 in 3. m2g minus m1a is equal to m2a. m2g is equal to m1 plus m2 multiplied by a. A is equal to m2 upon m1 plus m2 g, that is equation number 4. Putting the value of a from 4 in equation 1, t is equal to m1 m2 upon m1 plus m2 multiplied by g. Case 3. In the below figure, all the surfaces are frictionless and string and pulley are light and frictionless. So free body diagram is shown in the figure. So for mass m1, we can write the equation as t minus m1g sine theta is equal to m1a, which is equation 1. Similarly, for the mass m2, we can write m2g sine beta minus t is equal to m2a, which is equation number 2. And adding equation 1 and 2, we get m1 plus m2a is equal to m2 sine beta minus m1 sine alpha g. A is equal to m2 sine beta minus m1 sine alpha upon m1 plus m2 multiplied by g in the numerator. This is equation 3. And putting the value of 3 in equation 1, we find the value of t as m1 multiplied by m2 multiplied by sine alpha plus sine beta multiplied by g upon m1 plus m2. Now let us see few objective questions for Neet and IIT JEE and other competitive examinations. So the first problem is, a block of mass 2 kg is resting on a frictionless plane. It is struck by getting jet release water at 1 kg per second and it at a speed of 5 meter per second. Find the initial acceleration of the block. And options are A 1 meter per second square, B 2.5 meter per second square, C 5 meter per second square, D 0. So the solution is F is equal to, we know that force is equal to rate of change of momentum. So rate of change of momentum we can be written as mv, mass into velocity. So mass is written here, mass is written as delta m, and v, velocity is written as v, and rate of change, that is written as delta t, time. So putting the value instead of dm by dt, which is given here as 1 kg per second, we put the value of dm by dt as 1 kg per second, and we put the value of v, the speed, as 5, then we get 5 into 1, which is equal to 5 Newton. Therefore, we can find out the acceleration A is equal to F by m, that is 5 by 2, and the acceleration value is 2.5 meter per second square. So the option B is correct. Let us see the next problem. Here the problem is a pendulum is suspended from the roof of a compartment of a train and makes an angle of 3 degrees with the vertical. Find the acceleration of the train. Take 10, 3 degree is equal to pi by 60. Options are A 5 meter per second square, B 5.23 meter per second square, C 2.53 meter per second square, D 0.523 meter per second square. So solution is D. Now let us see the explanation of the solution from the figure of the free body diagram. mg is acting vertically downward. Tension can be divided into vertical and horizontal components. So the horizontal component is t sine 3 degree. Vertical component which balances the weight is t cos 3 degree. Then we can write that mg is equal to t sine 3 degree. ma is equal to t sine 3 degree. And mg is equal to t cos 3 degree. So dividing equation 1 by equation 2, we get A upon G is equal to tan 3 degree. Therefore, we can write A is equal to G tan 3 degree. Theta is small, so tan theta can be written in theta radian. Theta in radian. So A is equal to G. Instead of 10, we will write 3 up multiplied by pi upon 180. So instead of pi, we will write 3.14, and upon solving, we get 0.0523 meter per second square. So this is the answer. Next equation is a block A is able to slide on a frictionless inclined, inclined angle theta of length L kept inside the elevator going up with a uniform velocity v. Find the time taken by the block to slide down the length of the incline, and if released from rest, what would be the time taken if the elevator is accelerated at a meter per second square? Options are A under root 2L by G sine theta multiplied by 2L by G plus A sine theta. B under root 2L by G sine theta multiplied by 2L by G minus A sine theta. C under root 2L by G sine theta multiplied by, or comma, under root 2L G sine theta. D none of these. Here the solution is A. Case 1, we have half g sine theta t square is equal to 1. So t is equal to under root 2L g sine theta, 12 upon g sine theta. Case 2 is equal to half g plus a sine theta t square is equal to 1. Therefore, we can write T is equal to under root 2L upon G plus A sine theta. So the option is A. Next question. The magnitude of a force acting on a body varies with time as shown in the figure. The magnitude of rate of change of acceleration at a point is where mass of the body is 10 to the power 3. Options are given. A 3 multiplied by 10 to the power 4 meter per second cube. B 30 multiplied by 10 to the power 4 meter per second cube. C 8 multiplied by 10 to the power 4 meter per second cube. D 80 multiplied by 10 to the power 4 meter per second cube. Option is B and C. Let us see how. Rate of change of acceleration for A, B is 0. Rate of change of acceleration for BC is 800 minus 200 upon 2 multiplied by 10 to the power 6 multiplied by 10 to the power 3. From the graph, we get the figures. So upon solving, we get 30 multiplied by 10 to the power 4 meter per second cube. Rate of change of acceleration for CD is equal to 800 minus 0 upon 10 into 10 to the power 6, 10 to the minus 6 multiplied by 10 to the power 3, that is 8 multiplied by 10 to the power 4 meter per second cube. Next question is, an iron nail is dropped from a height h from a surface of sandbed. If it penetrates through a distance of x in the sand before coming to rest, the average force exerted by the sand on the nail is option A mg h upon x plus 1, B mg x upon h plus 1, C mg h upon x minus 1, D mg x upon h minus 1. The solution is A. Let us see how it came. The nail hits the sand with a velocity v0 after falling through the ceiling at a height h. So v0 square is equal to 2gh, that is v0 is equal to under root 2gh. This is equation 1. The nail stopped after a time t penetrating a distance x into the sand. Since the velocity decreases gradually, the sand extracts a retarding upward force R. The net force acting on the nail is given as sigma Fy is equal to R minus mg, that is equal to ma. Therefore, R is equal to mg plus a. This is equation 2, where a is the acceleration of the nail. Since the nail penetrates a distance x, therefore 0 minus v naught square is equal to minus 2ax. This is equation 3. Putting v naught from equation 1 and a from equation 2 in 3, we obtain 2gh is equal to 2 r minus mg upon m multiplied by x, which implies that r is equal to mg h plus x upon x. R is equal to mg common h upon x plus 1. And this is the end of today's class. Before closing the session, we request you to subscribe, like, and share our channel among your friends and relatives. And please click on the subscribe button to support us, and click on the bell icon to get automatic notification whenever a new video is uploaded by us. We'll continue this session in the next class when the second part will be released. Until then, have a happy weekend. Thank you very much.